So Unit 8 is really on applying mostly the fundamental theorem of calculus. And integrals. I would probably say applying integrals and the fundamental theorem of calculus. This lesson, I forgot about you. Sorry. This lesson is just applying the fundamental theorem of calculus, okay? And we're going to start by understanding differential equations and how to solve them. We'll solve a couple differential equations. Like we're used to, you guys know how to solve differential equations. There were a couple questions on the test and on your quizzes. But now we're going to figure out another way to do it, okay? So let's remember, a differential equation is just an equation with a derivative, or it's just, it's almost like just a bunch of initial conditions, including an equation with derivative. And then when I asked you to solve a differential equation, what were you asked to do?
Find the base f of x.
Exactly. Find the function whose derivative is given and that also satisfies those initial conditions. So like find where you start with. Okay, now this is a differential equation, but there's an extra step. So I'm going to kind of get rid of the extra step for now, and I'm going to bring it back. So I could ask you to find f of x, given f of 1 is 3 and f prime of x is equal to 4x plus 2. You guys go do that. Okay, we start by taking the antiderivative of 4x plus 2, which is 2x squared plus 2x. Don't forget your c. And then we plug in 1 and 3 to find c. 3 is equal to 2 plus 2 plus c. c is equal to negative 1. And we get f of x is equal to 2x squared plus 2x minus 1. Okay? That's solving a differential equation. Well, I could kind of ask the same question, but instead of find f of x, I could just say find f of 4. Well, you've already done all of the work. There's just one extra step. So this question, though it's not solve the differential equation and find f, it's saying find f of 4. Well, the only way you can do that is by solving the differential equation, and then you can go ahead and plug 4 in. So figure out what f of 4 is. Just an extra little step. We get 16 times 2 is 32, plus 8 minus 1, that's 39. Okay, so we did it. Let's do another one just like that. This one. F prime of x is equal to 6 root x and f4 equals 3. I want you to find f9. You don't need your calculator to find 4 to the 3 halves. Or 9 to the 3 halves. This is negative 29. $98, $78, $68. Wait. Yeah. $79. What? Yep. Right, not bad. You know, it won't work though. A lot of steps here, a lot of calculations, but not bad. Okay. Well, let's try one more. Let's do this one. All right, what happens? What's going on? What can't we do? What are we struggling with? Yeah, we can't do, there's no product antiderivative of the product rule here. So it's like, I do not know what this is. If I end up taking the BC test, I will have to know how to do this. But everybody else, no. So it's just like, well, it's like, this is unsolvable. Well, actually it is. Okay, it's very solvable. And the last 2 problems that we just did, we can actually do that a different way and a quicker way. Okay, so long as we have our calculators. And let me show you. Let's kind of do a little kind of pause on these differential equations, and let's find areas under curves using our calculators. Okay, your calculator can find the exact area under the curve. So say the area from 0 to 4 of x squared dx. Now, how do you guys know how to find the area under x squared from 0 to 4? Yeah, you're finding the change in the antiderivative, right? So that's the whole fundamental theorem of calculus. You say, all right, find the change in the antiderivative. That's the exact same thing as the area under x squared. So 1/3 x cubed, plug in 4, plug in 0. It's not that bad, right? Well, your calculator doesn't know how to take antiderivatives. Can't do that. However, it can make lots and lots of calculations really, really quickly. You know, computer systems. They can do things really, really fast that we can't. So what your calculator can do with this x squared is they can say, all right, I can find the function values of x squared, and I can just denote a delta x that's really, really small, and I can actually make a lot of rectangles, so many rectangles that my area is pretty much essentially going to be the exact thing. That's what your calculator is. That's what we could have done, just we don't have time to do that by hand. Okay? Lots and lots. I don't even know what their delta x that they use is. It might be like 0.01, 0.001, but that's what they do. They just take x's, bases times heights, and they give you an answer. How do you have your calculator give you this answer? You go to math, and you go down to 9, F-N-I-N-T. We know n derive is take the derivative. F-N-I-N-T is your integral or find your area. Okay? Now, some of you, the notation that you see right here pops up. This is a piece of cake for you. You can just type in what you see. Some of you, the F-N-I-N-T pops up. For those of you who have the F-N-I-N-T that pops up, this is the order, and you should probably write this down, that you need to type things in. You're going to take the integral of whatever your function is. So in this situation, I'm taking the integral of x squared. Then you have to say it's going to be with respect to a specific variable, with respect to x. So you say comma with respect to x. Then you will give its intervals. You will say from a, comma, to b. And then you press enter, and then you rejoice that you don't have to find the antiderivative and plug things in. Okay? (64 thirds). Okay? Well, now we know how to find areas under curves using a calculator. Now we don't even need the fundamental theorem of calculus if we have a calculator for a problem like this. All we need is a calculator. Now, of course, we didn't have our calculator, and I didn't teach you how to do this last test, and the whole non-calculator part was things that you could do with your calculator. Notice a lot of the questions involved on the test, even if you had your calculator, you wouldn't be able to figure it out. You had to understand the fundamental theorem of calculus. So that's why you didn't know that until now. But right now, you do need to know this, because knowing how to find areas under curves using your calculator can help you figure this out. Can help you find f of 6 given f of 1 is equal to 1 and f prime of x is equal to x squared e dx, okay? Our calculator can help us. But now the question is how? How can it help? Because these differential equations, like this one, it seems impossible if I don't know how to find the antiderivative. Well, the fundamental theorem of calculus will be the key. The fundamental theorem of calculus says the area under a derivative function is equal to the change in its antiderivative. Area under f prime is equal to the change in f from A to B. Not the rate of change, not the change in the rate, it's just the change. It's just the overall numerical change. Well, could we use that fundamental theorem of calculus to help us solve that previous example that we couldn't because we couldn't find the antiderivative of x squared e to the x? How? Who can tell me what I should do?
A and B value.
What would the a and b value be?
6 and 1.
Yep, that would be right, but how's that help me? I got to find f of 6. And plug it into the derivative. That'll give me the slopes of the tangents. It won't help me with the function values. Simpler than that. Watch. What if I say f of 6 minus f of 1 equals the change from A to B of f prime? Add f of 1 to the other side. All of a sudden, if I add f1 to the other side, I get this equation. That's my future value that I'm trying to find, f of b, which is f of 6 right here. That's going to be equal to my initial value given. In this case, it's f of 1, or we could say it's f of a, plus the area under f prime, but don't think of it as the area under f prime. Think about that as being the change in f between a and b. Now, if you have a calculator, you don't care if you can find the antiderivative. You just take f of 1 and you add the area from 1 to 6 under f prime. Now I'm going to change this value actually because sometimes it can be confusing if we use the same values too many times. I'm going to change this value to 2. Okay, so everybody change that in your example to 2. All I'd have to do to find f of 6 is take my initial f of 1 value and add the change, which is the area under the derivative between 1 and 6. Or f of 6 equals 2 plus that. You guys figure out what that is. Well, x squared e to the x is a rapidly increasing function. So if you're talking about between 1 and 6, the area under x squared e to the x, yeah, that's probably pretty big. So really the 2 doesn't matter much, but it matters. Okay, so I just go plus math 9 FNINT x squared e to the x with respect to x from 1 to 6 is 10488.430. Either way, you should get 10488, right? Whether you add it at the beginning or at the end. Cool, huh? Well, do this example, the second example that we did that, it took up a lot of space, and solve this example again using this newly found way to find these future function values that we don't know. But we do know an initial value, and we do know the derivative. Make sure you see on your calculator the answer that you're supposed to see. Now, here's what trips people up. They think that if they want to find f of b, do I have space to write this on there? Some people say, okay, if I want to find f of b, I use f of a and then the area under f. This is wrong. It's not all in the same line. The area under f gives me the change in big F, right? Yes, that would be the change in big F. That does not give me the change in F. I need to find the change between A and B so that I can find what F of B is given F of A. So don't make this mistake and keep everything on the same kind of derivative line, F, F, F. It's got to be F, F, and its derivative. That is correct, okay? Because it's the derivative, the area under the derivative, that gives me the change in my function, my original function. That's the whole fundamental theorem of calculus. That's the beautiful thing about how we can find areas under curves if we just link things to antiderivatives. Okay? Cool. So keep that in mind and do this. Do it whatever way you want. I don't care. Check your answer with a neighbor. Two ways to do it. Really? You want to find the position at 2 pi over 3. You just take your position at time 0, which you know is -3, and add, not equals, add the area from 0 to 2 pi over 3 under the derivative of position, which is velocity. This is a quick way to do it using your calculator. We just get the value, what? 6. Now, this is cool to use if we had a calculator for this, but this is a question that you should be able to do without using this method. It just shows you that, you know, this is kind of quick. Probably preferred over the find C method. I call that like the original differential equation method. We're finding the antiderivative first. You find C, and I could show you that if I wanted to. And sometimes, like, you're going to forget about one or the other, so you got to have both. X of t would be equal to -6 cos t plus c. You would use x of 0 is equal to -3 to find c. And keep going. Okay? Cool. Let's give you a tough question. Let's get into some AP questions, okay? The AP test and the AP test graders use this application of the fundamental theorem of calculus so often. It's like the #1 thing once we start reviewing that I'll say, hey, don't forget this. Don't forget that a future value is equal to an initial value plus the change in, you know, the derivative, plus the change in those values. Okay? Now, read this question and just pause, and we're going to talk about it for a second, because this is an actual AP question from the past year. And delete that, doesn't make sense. And they use like specific notation really to kind of screw you up. Okay? Plant opens a day of 500 tons of coal, works an 8-hour workday. How many tons will the plant finish with at the end of the day if no coal is processed? So this is what a lot of people do. They say, okay, G of 8, that's going to be my answer. Just plug in 8 into that G function, and I will have the amount of coal that I've received. Is that correct? Is it G of 8 plus 500? Is that correct? It's not, but this is what everybody thinks. Everybody thinks it's just going to be G of 8 plus 500. And now the whole 500 should be kind of included in this function if this were true. And here's the ticket. This G, this capital G, it's a derivative. That is a rate at which the plant is receiving coal. It is not how much coal has been received. Think about it as not the population, but it's the change in the population. What you're given is the change of the population. So what G of 8 gives you is what? Not the answer or how much coal you've received total. What is G of 8? Yeah, the exact rate, the instantaneous rate that coal is coming in at that moment.
So
That's a derivative. It's a rate of change, a rate at a specific moment. So it's almost like, and you'll have to do this, you have to think about this, you're gonna be like, you know what? I'm gonna just put a prime there. I feel like there should be a prime there, so I'm gonna put a prime there. Okay? All of a sudden, G prime at 8, this makes sense. This is a rate, coal is being received at t equals 8. Does that make sense? Right? So its antiderivative would be G. If I change this to G prime and all of a sudden I look at G, its antiderivative, what would G be? If G prime is the rate that I'm receiving coal, what is G?
how much coal at that hour?
Just how much coal that you have. This would be like the total population, total coal received. And I know this regular G without the prime at 0 is 500. You guys tell me how much coal we have at the end of the 8-hour workday if no coal was processed. I want to see if I even wrote down the problem right. Maybe like it had a G prime to begin with. Can't find it. There it is, 2013. There it is. No. See, this is funny. What do we get? 13 something?
13.25.
Good. 1325. This is just G of 8 is equal to G of 0 plus the area from 0 to 8 under what we consider G prime. So this is 500 plus whatever it is, and you get 13. What is it?
1325.55.
Okay. So, what if 100 tons of coal was processed per hour? How much coal would we end up with? Good. What do? We subtract 800. 100 tons of coal processed per hour, 8 hours. Good. Let's read the entire question on the 2003 AP Calculus exam. On a certain workday, the rate in tons per hour at which unprocessed gravel arrives at a gravel processing plant is modeled by that. This is gravel, not coal. Where T is measured in hours, and we're looking from 0 to 8. At the beginning of the workday T equals 0, the plant has 500 tons of unprocessed gravel. During the hours of operation 0 to 8, the plant processes gravel at a constant rate of 100 tons per hour. So just like what we did. Now, part A. Find G prime of 5. Use correct units. Interpret your answer in the context of the problem. Go. This is the whole, interpret your answer in the context of the problem that starts to pop up more and more now that we're talking about applying the knowledge that we know. If you don't understand what G means for A, B, C, and D, it's going to be a struggle for you. Let's see, G prime of 5. This would be negative 45 sine of T squared over 18 times 2T over 18. And then you'd plug in 5. You could probably use your calculator for this, so let's just do that. So that would be the derivative. So let's go math 8 and derive of your function when T equals 5.
2T over 18, that's not the derivative of the inside.
Yes.
It is?
Yes. With respect to x at 5. Negative 24.587. Somebody confirm that. That's correct. Okay. Okay. All right, what does that mean? And what are the units?
Instantaneous rate of change of the instantaneous rate of change of gravel volume.
That's exactly right. It's the rate of change of the rate that gravel is being brought in. So you're bringing in gravel at a rate, say you're always bringing in gravel, so it goes from 5 tons to 105 tons. You're looking at the change in that rate. So since it's negative, you would say the rate at which gravel is arriving is decreasing by 24.58. What is the notation? What is the unit?
Tons per hour squared.
It would be tons per hour squared. You'd think about it as acceleration. If this is velocity, this is tons per hour. This would be tons per hour squared. Woo! Okay, so that's automatically tricky. Part B, how would you find part B? Find the total amount of unprocessed gravel that arrives at the plant during the hours of operation on the workday.
same thing as the first part we did, just put up 500.
Exactly. It would just be the change from 0 to 8 of g of t, or the area under g of t. Now, of course, they're telling you g, it's not g prime. You got to almost come up with a different function. You could say like p of t is equal to the total gravel. And you would have to say, okay, the connection is that p prime is equal to g. Whew. All right? This is what you're expected to know how to do come May 4th. All right, part C. Is the amount of unprocessed gravel at the plant increasing or decreasing at time t equals 5 hours? Show the work that leads to your answer. Almost. No.
They have 100.
Yes, that's exactly what you're doing. Are we increasing or decreasing? Well, we have to check to see is the gravel coming in more than the gravel coming out. G of 5 is the rate that the gravel's coming in. And 100 is the rate at which the gravel is going out. So you got to find G of 5 and compare it to 100. So what's G of 5? Plug it into your calculator.
98.14.
So are we increasing or decreasing? Decreasing, because the 100 is bigger than G of 5. And then finally, what is the maximum amount of unprocessed gravel at the plant during the hours of operation on this workday? Justify your answer. Oof. How do we find maximum amounts? Find the relative extrema, right? How do you find the relative extrema of something? Well, the derivative equals 0. Okay, so if I want to find the maximum amount of gravel, this is the total amount of gravel, the P of T. If I want to find the maximum amount of gravel, I got to figure out when P prime is equal to 0. Well, P prime is equal to what? G. So it turns out I just need to figure out when G is equal to 0. If I figure that out, and I notice that that is just a maximum, a relative maximum, boom, I get the right answer. And you'll be able to use your calculator in that. You'll be able to graph. You'll be able to see between 0 and 8 when it crosses the x-axis. And you'd be able to then find that that's a maximum. And they don't ask you, no, they ask you for the maximum amount. So once you find the time, great. You'd find T, and then it would be G of that value would be equal to 500 plus the area from 0 to that value under, and of course this is P. Gosh, what? I really screw you up with that stuff. G of T. Just kind of want to show you this to introduce the types of questions you'll see moving forward. Okay, I'll tell you that the review for this test coming up are just all AP style questions, because you're going to start to see AP style questions on your tests. Like very, very much like this style, AP style questions. Okay, this is when things get a little trickier. But you just got to really understand your concepts, and if you understand your concepts, you'll be okay. Let's do another one like that. Fun. This one's a little bit easier. This is another calculator question. Go. Read the question. Find an answer. Check with a neighbor. Still working. I must have plugged something in wrong. The negative x squared. Yep. I feel like my calculator almost broke there. Jeez. S of 10. Oh, jeez. That's why I broke my calculator. So, of course, if this was S of t, they'd want a t here. This would be the answer to the first part. And then particle at time 5, 10 plus 0 to 5 of v of t. Second entry. Negative 9.207. All right, cool. One more. This data should seem familiar. You saw this data on your test. Well, you did part A on your test. This is part B from the AP test. You guys can do part B right now. Part B right now. Ready, set, go. If you get like 74 something, no. Not right. You got to read the fine print closer if you got 74. Read the fine print closer. Got it? To find W of 25, that would be W at some initial value plus the change, which is the area under the derivative. Well, you have W prime. The key is this W prime only works for t greater than 20, less than 25. So you would not use that the initial temperature is 55. That is misleading. You'd use the temperature at time 20 is 71. You'd say W at 25 is equal to W at 20 plus the change, which is the area under W prime. Okay. Let's see if we have any others. Yes, this one. I want you guys to do this one. This is the last one. Only if everybody works on it. For t from 0 to 6, the particle is moving along the x-axis. The particle's position is not explicitly given. The velocity of the particle is given by that function. The acceleration of the particle also is given. And we are told that my position at time 0 is 2. For t from 0 to 6, the particle changes direction exactly once. Find the position of the particle at that time. Let's see if you can figure it out. This is a heavy calculator usage problem.
Is that t over 4 above the e?
Yes, that's 2 sine e to the t over 4. Let me do it real quick. See if you guys can get the answers. when would we be able to, or what do we have to analyze to see when a particle changes direction? When velocity changes sign. Okay. So that's step one. You need to figure out when velocity changes sign. You don't want to set velocity equal to 0 and solve that by hand. I'm not going to solve sine e to the t over 4 plus 1 by hand, equals 0 by hand. So instead, you graph your velocity, and looking at your graph, you see where it crosses the x-axis. And when your velocity goes from positive to negative or negative to positive, that's when you change direction. So start by doing that to find t.
So the acceleration part of the question is
Or just to confuse you. Maybe, you know what, maybe there's another part, probably, Mr. Barron, that says, is the speed of the particle increasing at t equals 4? And what would you have to do to examine the speed of the particle? What do I have to analyze for speed? Right? Exactly, right? The signs are the same. So the next question might be like, when the particle changes direction, well, velocity is going to be 0, so it's not going to be speeding up or slowing down. But anyways. Does everybody figure out 5.1955? Did everybody find that? Second calc intersect. You got to be able to find the exact solution. You can't find an approximation. So how do you find the intersection? Graph the velocity curve and y equals 0 and second calc intersect. That's something we have to be able to do. Once you find that intersection, that 5.1955223, then you need to find the position at that point. Well, I don't have the position function, so I have to use the fundamental theorem of calculus and say my position at this time has to be equal to my initial position plus the change, which is the area under my velocity curve, from 0 to that 5.19. You get that. Make sure you understand how to do this. Any questions? Oh, thanks. Okay. So, to figure out when velocity is changing directions, graph your velocity. Make sure you plug it in correctly. And then you want to probably adjust your window to be from 0 to 6 just to make things easier. Because it says between 0 and 6 it does once. And you should also graph y equals 0 so you can find the intersection. Okay, now the goal is to find that intersection right there. So second, calculate the intersection. If you graph y equals 0, you can do that. No, so now that I have the time to find the position, I need to do my position at this time is equal to my initial position, which is given to me, plus the change in the position, which is the area under your velocity curve, which is the derivative of position. Okay? Does everybody have the homework? The homework's online. If you don't have it. It's your first worksheet. Second worksheet of the year. Enjoy it.